Hello children, we are going to continue with exercise 1.3 from chapter number 1 real numbers and solve the remaining examples. So this is question number 2 from exercise 1.3, and from question number 2 this is the third sum. If you remember, in the previous video lesson I told you one particular sum which is very important, that is to prove that root 5 is an irrational number. Similar to that sum, here we have another example. Prove that 3 plus 2 root 5 is an irrational number. Now, I told you that such type of sums we have to solve by the method of assumption, and here we will assume exactly opposite to what we have given. We are given that 3 plus 2 root 5 is an irrational number, and we will consider exactly opposite to this, that 3 plus 2 root 5 is a rational number. And then we will check out that whether our assumption is correct or it is not true. So we will consider that 3 plus 2 root 5 is a rational number. As you all are aware, every rational number can be written in the form of a upon b, that is in the form of numerator upon denominator. So we will write our number 3 plus 2 root 5 is equal to a upon b, where a and b are co-prime numbers, and the meaning of co-prime numbers is they do not have any common factor other than 1. So 1 will be the only common factor between these two numbers. So we have considered a and b as co-primes. So let's write down 3 plus 2 root 5 is equal to a upon b. Alright, now we'll shift this 3 to right side. So we're left with 2 root 5 is equal to a upon b minus 3. Let's solve this right side. So 2 root 5 is equal to a minus 3b upon b. We have done a cross multiplication here. Let's move ahead. This is what we have written. So now what we'll do, we'll shift this 2 at the denominator. So we are left with square root 5 is equal to 1 upon 2 into a minus 3b upon b. So we can write it, root 5 is equal to a minus 3b upon 2b. Now check this expression carefully, children. Left hand side square root 5. We have already proved that square root 5 is an irrational number. But if you see the right side, the number is written in the form of numerator upon denominator. And any number which can be written in the form of numerator and denominator is a rational number. So what are we getting? We are getting that an irrational number is equal to rational number, which is absolutely wrong. Rational number and irrational number cannot be equal. Alright, so this is the contradiction to what we have assumed. So our assumption that 3 plus 2 root 5 is a rational number is incorrect. It's not right, and therefore we can say that 3 plus 2 root 5 is an irrational number. So every time you are asked to prove that, show that this particular number is an irrational number, you have to always assume exactly opposite to that. You have to assume the number as a rational number, write it in the form of numerator upon denominator, and go on solving it. Alright, so let's go ahead. Let's move to the next sum. This is exercise 1.3, question number 3. So question number 3, we are asked, prove that the following are irrational, and the number given to us is 1 upon square root 2. So we have to prove that 1 upon square root 2 is an irrational number. As I told you, we will assume exactly opposite to this. So we will assume that 1 upon root 2 is a rational number. As you all know, every rational number can be written in the form of a upon b, that is numerator upon denominator, and both a and b are co-primes, that is they do not have common factor other than 1. That means 1 is the only common factor for such numbers. So we can write 1 upon 2 is equal to A upon B. Now what we will do, we will reverse the ratios. By reversing the ratios, we get B upon A is equal to square root 2. Now look at this expression carefully. If you see the left hand side, it's written in the form of numerator upon denominator. So we can say that this number is a rational number. And if you check the right hand side of the expression, square root 2 is an irrational number. So we are getting a rational number is equal to irrational number, which is absolutely wrong. Rational number cannot be equal to irrational number. And this is a contradiction to what we have assumed initially. We have assumed that 1 upon square root 2 is a rational number, and this is absolutely wrong. Our assumption is incorrect. And therefore we can say that 1 upon square root 2 is an irrational number. I hope you must have understood the steps which you have to follow when you have to show that a particular given number is an irrational number. It's very easy. So please go through such type of sums once again, because these are very important sums. So exercise 1.3, question number 1, 2 is very, very important for all of you. So now let's move ahead. Let's go to the next sum. This is question 1 from exercise 1.4. Question is, without actually performing the long division, state whether the following rational numbers will have a terminating decimal expansion or non-terminating repeating decimal expansion. Now see, we are not actually doing the division process. Then how will we come to know that whether the decimal expansion is terminating or non-terminating and repeating? For that, you have to follow two particular rules. And the rules are, you are given a number which will be in the form of P upon Q. P upon Q is terminating only if P and Q are co-primes. And meaning of co-primes, you are aware that they will not have any common factor other than 1. So this is the first rule, that both the numbers should be co-primes. And the second rule is that Q is of the form 2 raised to n, 5 raised to m. And what is Q? Q is the denominator. The number will be given to you in the form of P upon Q, where P is numerator, Q is denominator. Both the numbers should be co-prime, and the denominator, whatever will be the number at the denominator, it should be in the form of 2 raised to n into 5 raised to m, where n and m are non-negative integers. So if the given fraction follows these two rules, that means the decimal expansion of the number is terminating. If it doesn't follow the rules, that means the decimal expansion is non-terminating and repeating. So let's see the example. This is 1.4, question number 1 and first sum. The number is 12 upon 3125. Now let's first check for whether these two numbers are co-prime. Yes, we can make out 12 and 3125 both have no common factors other than 1. And therefore we can say that they are co-prime number. So the first rule is applicable here. Now the second rule is denominator should be in the form of 2 raised to n into 5 raised to m. Now for that we need to factorize the denominator. So the denominator is 3125. Let's start factorizing this. So we can make use of our old method of factorizing the number. Either you can make use of the vertical method or the horizontal method, that is absolutely your choice. We have made use of the vertical method. So let's start with 5. So this is 5, 6 are 30, then 5 2s are 10, and then 5 5s are 25. Again we can just start with 5. So 5 into 125 is 625. Again 5 into 25, then 5 5s are 25, and then 5 1s are 5. So the factors of the denominator 3125 is equal to 5 raised to 5. Now this 5 raised to 5 we can write in the form 1 into 5 raised to 5. 1 I can write in the form 2 raised to 0. Any number raised to power 0 is 1. So in place of 1 I can write 2 raised to 0 into 5 raised to 5. So the denominator is of the form 2 raised to n 5 raised to m. And what is the value of n? N is 0 and m is 5. Since the denominator is of the form of 2 raised to n 5 raised to m, we can say that 13 upon 3125 is a terminating decimal. The decimal expansion of this fraction is terminating. So this is how, without actually doing the division process, we can find out whether the decimal expansion is terminating or non-terminating and repeating. Let's see another example. So this is the second question, 17 upon 8. Now clearly we can make out that 17 and 8 have no common factors other than 1. So they are co-prime numbers. First rule is verified. What about the second rule? So let's check for the denominator. Denominator is 8. You can factorize 8 as 2 into 2 into 2. That is 2 cube. I can write 2 cube as 1 into 2 raised to 3. And I can write that as 5 raised to 0 into 2 raised to 3. Because 1 we can write in the form of 5 raised to 0. Because 5 raised to 0 is 1. So we can see that the denominator is in the form of 2 raised to n 5 raised to m, where n is 3 and m is equal to 0. Hence we can say that 17 upon 8 has a terminating decimal expansion. Alright, so I think it's very easy to understand. There is nothing hardcore to understand the sum. It's very simple, and such type of sums may come for 1 mark in the exam. Let's go ahead and solve the next sum. So the next fraction given to us is 64 upon 455. This is third sum, exercise 1.4, question number 1. 64 upon 455. Clearly, if we check for whether they are co-prime, we can make out that they have no common factors other than 1. So 64 and 455 are co-prime numbers. First rule is verified. What about the denominator now? Let's start factorizing the denominator, that is 455. We can start with 5. So 5 into 91, then 7 into 13, then 13 ones up. So the factors of 455 are 5 into 7 into 13. Now we can check out that the denominator is not of the form 2 raised to n 5 raised to m. We have only 5 there. 2 is missing. Since it is not of the form 2 raised to n 5 raised to m, therefore the decimal expansion of 64 upon 455 is non-terminating and repeating. Alright, so if any given fraction follows the two rules that the numbers are co-primes and the denominator of the fraction is of the form 2 raised to n 5 raised to m. Alright, let's move ahead and solve the next sum. The next fraction which is given to us is 15 upon 1600. Children, I forgot to tell all of you that when the fraction is given to you, first you check out can you reduce it to the lower terms, which will make your sum simple. So here I can do that. 16, you can reduce it to lower term and we get the fraction as 3 upon 320. You reduce it with 5 3s are 15 and 5 320s are 1600. So now our fraction is 3 upon 320. So we can make out that 3 upon 320, 3 and 320 both are co-prime numbers because they don't have any factor which is common other than 1. Let's check for the denominator now. 320 is the denominator. Let's factorize it. So we will start with 2 into 160, again 2 into 80, again 2 into 40, 2 into 20, 2 into 10, 2 into 5, and then 5 ones are 5. So the denominator 320 has factors 2 into 2 into 2 into 2 into 2 into 2 into 5. I can write it as 2 raised to 6 into 5 raised to 1. So the denominator is of the form 2 raised to n into 5 raised to m, where n is 6 and m is 1, and therefore we can say that this fraction 3 upon 20, that is 15 upon 1600, has the terminating decimal expansion. Alright, so easy to understand. I hope you all will be able to do it. Along with this, you have an assignment. I want all of you to solve these 2 questions and try and check out whether you're getting the answers. Prove that the following are irrationals, wherein you have to follow the steps which I have explained you, and in the second case, without actually performing the long division method, you have to check whether the decimal expansion is terminating or non-terminating and repeating by following the 2 rules. Alright, see you all in the next video lesson. Until then, keep solving the sums. Bye and take care.